So this is free response question number 6 from the 2010 AB exam. This was Form B of the exam. And the situation that's described is that we've got two particles moving along the x-axis. For the time interval from 0 to 6, particle P has its position given by this function, while the position of particle R is going to be given by this function. And then in part A here it says, on the interval 0 to 6, find all times t during which particle R is moving to the right. So particle R is going to be moving to the right when its velocity is greater than 0. Right? R is moving to the right if the velocity is positive for R. If the velocity is negative for R, then R is moving to the left. Particle R is moving to the left. I think what makes the most sense to do here in order to determine this is, since the derivative of position is going to indicate a velocity function, like the velocity formula for R, so I'm just going to label this as V sub R of t, this is going to correspond to R prime of t. And R prime of t is pretty simple to find, right? We're just going to use the power rule. So if we take the derivative of this, we're looking at 3t squared minus 12t and then plus 9. So there's our velocity formula for particle R. What we want to do is we want to figure out when this velocity is positive. So I think it makes sense just to try to build a little sign chart for R prime that's going to hold on the interval from 0 to 6. Right, so I'm looking at a sign chart for R prime of t that we're trying to construct right here. And so whenever we build a sign chart, we like to know when the sign of our derivative is able to potentially change, and that's any time when the derivative is first equal to 0 or undefined. Now if you look at this derivative is never going to be undefined. This is a polynomial, and a polynomial is always going to be defined. So really we just have to figure out when our derivative is equal to 0. And this doesn't look like something that I'd want to try to isolate t in. I'm going to want to solve this by factoring. So if I went ahead and noticed that 3 is a GCF, I can take a 3 out of all of my terms. And that should make what follows a little bit easier. So we take 3 out of everything and we're left with this. And then that set of parentheses will factor a little bit further. I think we'd be looking at t minus 3 and t minus 1 as the factors of this polynomial right here. And so if we set this factor, t minus 3, equal to 0, we would figure out that it is 0 when t is equal to 3, and if we set this factor equal to 0, we would see that it's equal to 0 when t is equal to 1. And so we have two places where the sign of our derivative can change in between 0 and 6. The first one is positive 1, so I'm just going to have a possible change in the sign of the derivative as we cross positive 1, and another possible change as we cross the t value of positive 3. And so if we pick a test value from this piece of the number line, if we pick a value like 1/2, here is the form of the derivative I'm going to plug into. If I put 1/2 in place of this t and in place of this t, I'm looking at 1/2 minus 3 giving me a negative value. I'm looking at 1/2 minus 1 giving me a negative value. Positive times a negative gives me a positive value for the derivative. In between 1 and 3, if we go with a value like 2, 2 minus 3 is negative, 2 minus 1 is positive. So we have positive times positive. That's going to give us a negative product. And then on the interval from 3 to 6, if you pick a value like 5, this factor is positive, this factor is positive. Positive times positive is going to give us a positive answer. And so our velocity for particle R is positive between 0 and 1. It's positive between 3 and 6. So particle R is moving to the right on this interval and on this interval. And the reason why is because the velocity for particle R is positive on both of those intervals. In part B, we want to determine all times during which the two particles are traveling in opposite directions. What I'm going to do is I'm actually going to go back to part A here and steal this sign chart, because this sign chart is essentially going to tell us when particle R is moving to the right and when particle R is moving to the left. So if I go ahead and try to copy this to this new screen, we're basically going to want to take a little bit of time to do the same thing to particle P. So we'll go ahead and steal this from part A. And now we'll do a little bit of work to see if we can figure out when particle P is moving to the left and moving to the right by trying to construct a sign chart for it. So the velocity of particle P is going to be given by P prime of T. And P prime of T is going to have a constant of 2 that just gets copied into the derivative. The derivative of cosine is negative sine. And then what I need inside this negative sine function is this inner function. So pi by 4 times t, the inner function stays there. And then we're going to have to finish this derivative by multiplying by the derivative of this inner function. Well, the derivative of a number times t is just going to be the number, so the derivative of our inner function is going to be pi by 4. What we want to try to do is we want to try to construct a sign chart for P prime of t. So I'm going to try to build this in the same way that we built the one for R prime of t in part A. So we're looking for the sign of P prime of t. And we need to know when the sign of P prime of t can potentially change on the interval from t equals 0 to t equals 6. So it can change if the derivative is first undefined. Now if you check out this derivative, it's never undefined. Sine is always defined. The expression inside the sine function is always defined. And so what we can go ahead and do is we can just set this derivative equal to 0. And we can try to, let's see, if I simplify this, I'm going to pull this negative 1 out in front of the 2. And then I'm also going to pull the pi by 4 that's at the end of this out in front. And I'm basically looking at this as a factored form of this derivative, right? It's negative 2 times pi by 4 times sine of pi by 4 over t. This factor is never 0. This factor is never 0. So we need to figure out when this last factor is 0. So we need to figure out when sine of pi by 4 times t is equal to 0. We need to figure out what values of t make this true. And what I'm going to use to help me out here is I'm going to use the unit circle. So if I use the unit circle on the interval from 0 to 6, I want to know when sine of pi by 4 times t is 0. Well, the sine function is 0 if we are at the angle of 0 or if we are at the angle of pi, right? If we think about when pi by 4 times t equals 0, so I'm basically trying to determine what values of t would make this angle inside the sine function equal this angle on the unit circle. I would get t equals 0. Well, that's already represented on our sign chart. That's kind of the left end point. And then I think I would be back to this angle right here if pi by 4 times t were equal to 2 pi. So when is this going to be true? Well, if we wanted to solve this for t, we would basically multiply by 4 and divide by pi, and that's going to give us t is equal to 8. So we're back to this angle when t is equal to 8, but that's outside the interval that we're supposed to consider. So we don't have really any values between 0 and 6 other than at 0 that make this angle inside the sine function end up at this spot on the unit circle. What about ending up at this spot? Well, that as an angle on the unit circle would be pi. And so if we try to set what's inside the sine function, pi by 4 times t, if we try to set that equal to pi, if you multiply by 4 and divide by pi, what you end up with is you end up with t is equal to 4. So if t is equal to 4, the angle in here ends up being pi, and sine of pi is going to end up being 0. So the only place where the sign of our derivative could potentially change is at the t value of 4. So if we pick the t value here, a t value like, say, 2, if we put 2 in place of the t in our derivative, this is negative, this is positive, and then the sign of pi by 4 times 2. Well, pi by 4 times 2 is pi by 2. Sine of pi by 2 is going to correspond to the y coordinate right there, which is 1. And so that ends up being a negative times a positive, which gives us a negative value for our derivative. And then on the other side, if we pick a value like 5, if we put 5 right here, sine of pi by 4 times 5, well, that's sine of 5 pi by 4. This is 4 pi by 4. 5 pi by 4 would be right here. Now, the value of the sine function right there, since it corresponds to the y-coordinate of that point on the unit circle, we know that the y-coordinate is negative since we're below the t-axis, or excuse me, below the x-axis there. And so we know we have a negative times a positive times a negative value for the sine function when 5 goes in place of t. The product of a negative, a positive, and a negative is going to be a positive. So when do the particles move in opposite directions? Well, they're moving in opposite directions on the interval from 0 to 1, right? Because on the interval from 0 to 1, particle r is moving to the right and particle p is moving to the left, right? Positive velocity, negative velocity. And then from 1 to 3, they're moving in the same direction, right? Particle r is moving to the left, particle p is also moving to the left. But then from 3 to 4, particle r is moving to the right now, and particle p is still moving to the left. So from 3 to 4, they're moving in opposite directions. And then from 4 to 6, they're both moving in the positive direction. So these would be the two time frames when the objects are moving in opposite directions. We'll finish the other two pieces of this in a separate video.